Hello and welcome back. In this video we will start section 10.2, which will carry on from last time, looking at linear correlation. And now we will begin to draw lines that describe the linear correlation. So the regression line is the straight line that sort of best describes linearly correlated data. And before I go any further, the regression line is often called the line of best fit. And this is what I would normally see outside of a stats class in the news. Say a line of best fit would often be the terminology that I would see. And the term best here is a little bit ambiguous or ill-defined, and I will define this later. But essentially, best, there is a process through which we will determine sort of numerically, according to this process, what line best fits the data. So just as an example, we can see that we have some like a scatter plot here. We have our x and our y, and we can draw a line of best fit. It'll be something like this. So we can see that this is roughly going to be a line that pretty much matches the data as far as describing the linear relationship here. It's going up and to the right, and in order to describe a line, a straight line, we need two things. One is where the line hits the y-axis, and this will correspond to B naught right here. And the second thing that we need to do is know sort of what angle is our line pointing. Is it going up quite fast, as in is it pointing nearly straight up? Is it almost flat? Is it pointing down? And this sort of angle, this is called the slope of the line, and that is B1 right here. So this equation is called the regression equation, and this describes this line. B naught will be this point there. B1 is describing how fast this is either going up or going down. So if you give me an x value, if we want a particular value for x, I can plug it into the equation, and I will know exactly where along this line I am. So in this system, I'm treating x as the independent variable, and y is the dependent variable. And these names come from the following. We normally think of we are given x and we have to figure out y. So y depends on what x is, but we can pick whatever value for x we want. It is independent of anything else. In this equation, I've used y hat when y is the variable, and y hat is going to be the predicted value of y based on our equation. So whereas y will correspond to actual data values, y hat is this prediction, and we just hope that our prediction is accurate. So in order to really find these regression lines, there will be a couple of requirements, and so let me go through those requirements really quick. These are the same requirements as we've been seeing before. We require that our line is based off of simple random samples, and then 2 and 3, a lot like last time. Visually, the scatter plot must look linear. This is quite vague and subjective. There are more objective ways to describe this, but essentially, if the scatter plot doesn't look linear, if it looks like it's sort of wiggling around or there's not a whole lot of correlation, then finding the line of best fit doesn't really make sense to do, sort of mathematically speaking. And we have to consider the effects of outliers. So I drew a couple of things, just a couple of examples here. If you were to draw the line of best fit through this data, we can see that, well, that line of best fit is going to be pretty accurate as far as it's going straight through those. But if you include this one outlier in there, now where does the line of best fit kind of go? It'll have to sort of go up to sort of get close to all of the points, and it's now not really close to any of them. It's pretty far away from all of them. Where over here, it was really close to every single one. So the fact that we have this outlier up here really threw off this line. So outliers can really affect the regression line. So we do want to be careful. If there are if there are a couple of outliers, we have to take our results with a grain of salt, because they could be thrown off by even the presence of just one outlier. And then very briefly, what I had skipped before was we do have a little bit of different notation when we're looking at a sample regression line and a population regression line. For samples, we use B0 and B1 to indicate the y-intercept, so where the line will hit the y-axis, and B1 for the slope, which is sort of the angle the line is at. Whereas for the population, just like with a couple of other letters, we use the Greek letter beta instead of B for the population. So it's beta naught and beta 1 for the regression line. And if we're talking about the whole population, we don't have predicted values anymore, because it's just exactly those data values. So we would just use y instead of y hat. So let's look at the formulas for these guys. They are not too bad. The formula for B1, which is a slope, down here is the y-intercept. Got to write that in. So for the slope, B1, this is going to be r times s of x divided by s of y. So sx and sy are just going to be the standard deviations from our samples. And r is going to be the linear correlation coefficient. So remember that r from the last section tells you how strong the linear correlation is. If it's very linearly correlated, if it almost lies exactly on a straight line, r is going to be close to 1 or negative 1. If it doesn't really look like a line, if it doesn't look very linearly correlated, r is going to be close to 0. So so r is just telling us how linearly correlated the data are. So so that's the slope, and then the y-intercept. Again, we just take the mean value of y and we subtract the slope times the mean value of x. And this essentially just comes from solving the regression equation. If we solve this for B0, if I just try to get B0 by itself, we can see that this will look very, very similar to this guy here. Now the computer will use some slightly bigger, messier formulas, B1 and B0, so the slope and the y-intercept, are given here. These equations we won't use, and we will in fact just use StatCrunch to calculate these guys. So let's go through and actually calculate a line of regression and look at a picture. So I say listed below, and by listed below I mean in StatCrunch I have some values, and it's the number of chirps in 1 minute by sort of a cricket recorded at a particular temperature in Fahrenheit. So it's known that crickets will chirp faster when it's hotter out. So you can somewhat accurately predict the temperature outside if you can count how many cricket chirps there are in a minute. So what we want to do is find the regression line so that we can predict these things. So let's come to StatCrunch. So we have six different recordings. The first column is just how many times the cricket chirped in a minute, or how the total total chirps. I think maybe this is for multiple crickets, and the average temperature over that minute. So I think one nice thing to do first, if we come over to graph, and we can actually plot the scatter plot for this data, so that we can look to see, is it actually a line, or does it not even look like a line? So our x value is just going to be the number of chirps in 1 minute, and our y value is going to be the temperature. So what we would like to do is have the chirps be the independent variable, the temperature be the dependent variable, so that if I give you how many times the crickets are chirping in a minute, you can figure out the temperature. I'm not going to change any of the other options here, and I'll click compute, and we have our scatter plot. And you can see that roughly this looks like a straight line. It's going up and to the right. So pretty linear. There aren't any outliers. Up here looks a little bit off, but overall quite linear. So let's apply regression. If we come to stat, and we can come down to regression, to be able to predict the line that would pass through this, we can come to simple linear, and we can try to create our line. So again, our x variable we want as the chirps. Our y variable we want the temperature. For the moment, we're not going to perform a hypothesis test or confidence intervals, but it automatically selects one. That's fine. We'll just leave that like that. Down here under graphs, I'm going to click on the fitted line plot. So this will actually plot the regression line for us, so that we can see what it looks like. And we will click compute. I haven't changed anything else, and let's see what happens. We have a lot of data here, so let's go through what's important and what we can ignore for the moment. So up here, our dependent variable is the temperature, and our independent variable is the chirps in 1 minute. So if you listen to the crickets chirp, we can determine what the temperature is. And then it gives this equation here, and this is our regression equation. This is saying that the temperature should be equal to 24.14, so that's 24 degrees Celsius, plus 0.056 about times how many chirps there were in 1 minute. So here is our regression equation. If the temperature was y and the chirps in 1 minute were x, y would be equal to 24 plus 0.05x. And then it comes down, it gives us our correlation coefficient, which is 0.96, which is very close to 1, which means that the data should be very linear. And then these numbers here, 24, we can read it off again as the intercept, and this 0.0566, this is the slope, and we can read it off again there. So it's the same things in a couple different places. So we have our equation, but we can also flip to the next screen and see it graphed for us. So again, here in blue are all 6 data points, and in red is the regression line for this. So I will stop here and talk about how to use the regression line and the regression equation in the next video.